I'm going to show you some examples, but before we get into the examples, I'd like to try to clarify the idea of PCl5. PCl, the periodic table wouldn't get out of the way. It was on my screen, but then when I processed it to a video, it wasn't. But here we are. We're going to do it again, and I'll make the best of it. But PCl5 had 5, and you're probably, what's with these 5 bonds here on PCl5? So the idea here is if you look at phosphorus, it's actually in the 3rd period. So that's why I had the periodic table there in the first place. I was pretty proud of myself to put that on there. But the idea here is that PCl, phosphorus especially, if you looked at the electron configuration, what you had was your 3s and your 3p, and that was 1, 2, 3, 4, and 5. You had 3 because it's in the 3rd position in family 5, family 15. Now the D's still exist. They're still here. They're out there. There's just nothing in them. So the question is, could we get this 1 electron over here to move right there? And the answer is no, not usually. But if there was this extremely electronegative element, let's say, I don't know, 5 of them, it could happen. And those electronegative elements could yank that right out. So that then gives us the opportunity for this electron 1, 2, 3, 4, and 5 now to be available for these 5 different bonds down here. So that's what I was trying to say. The periodic table got in the way, but hopefully it makes sense. It's all about the D block and its 5 orbitals. They're there. They're not being used. What could bring it out of them? What would bring it out? And that's basically what happened there. Okay. Okay, so let's pay attention to where selenium is in the periodic table because it's actually going to be what we just talked about. So if you look at selenium, it has 6 valence electrons. Okay, so we got plus 6 for oxygen, but there's 2 of them. So that's going to give us 18. And you learned at one time all we need to do. And all we need to do is make sure we start with single bonds. So we'll go ahead, let's just do that. Selenium's the less electronegative, we'll put that right there. So let's just do it. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. So that's not going to work. So go ahead and do, let's just take this guy right here and move it right there. So essentially what we're going to have is a double bond right here. Boom, boom. We have this right here, and this right here. Oxygen, oxygen. The only problem is when you bring this over here, now selenium has a lot. Really has a lot. So we have 1 or 2, 4, 6, 8, 10, and that's a lot. But the problem is also oxygen is over here, oxygen is over here. This is not a charged particle. There's no charged, there's not an ion. So we kind of want these oxygens to have equal access. And this one over here has too many. What if we did this? What if we did double bond, double bond? So we've used 8, right? Oxygen, oxygen, 2, 4, 6, 8, like I said, 10, 12, 14, 16. Everybody's happy, but remember, selenium could have 1 extra, like we said. So not only does selenium have access to 10 electrons, expanded octet, like we predicted based off of the last slide, but on top of that, oxygen has an equal number of electrons accessible. It's kind of that formal charge idea, but we didn't break it down and do the math. It's more of the eyeball test here. This works. Let's look at the next one here. The carbonate ion. So if we look at the carbonate ion here, we have 4 for carbon, 6 times 3, which is going to be give us a large number, plus 2. Don't forget about that. So that ends up being 24. So here on this one, this is different than the last one, and hopefully you're kind of seeing this. So the thing that's different about this is that we'll go ahead, okay, let's do our single bonds here, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. I don't think that works, though, because this carbon right here is missing one. So close. 24, we did it, but we didn't. Now notice that there's a charge right here. So I bet if we moved one of these right here, that would fix this problem. So again, here I go. I am going to do a double bond between the oxygen. I'm going to fulfill the oxygen. So I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24. There it is. I got it. This works, and I want to explain why. First of all, carbon's happy. It has access to 8. And this one does have more electrons than the other oxygens, kind of contradictory what I said the slide before. But remember, this is an ion, all right? The other thing you're probably saying is, wait a minute, can't this double bond actually move to this one? The answer is yes, and can't the double bond. So basically, we can have resonance. We can have several versions of this, just like we had in the video before. And so that actually works. We can have 3 versions of this. Okay, so we'd have to draw the arrows. We'd have to draw a version over here in brackets, and we'd have to draw a version over here in brackets too. But it does work. The next one is ClO1 negative. A little easier here. So what we're going to do with this one, we always have Cl with a charge, or excuse me, a valence of 7. We have oxygen with a valence of 6, but then we have to add that 1 electron to get 8. And this one's nice because we just say Cl. There's no middle. We just put 1 on one side, 1 on the other. Let's fill everybody's octet. And when we do that, we have 2, 4, 6, 8, 10, 12, 14, which I don't know why I put 8. That's 14 right there. So we're looking good on that one. But remember, anytime you have a charged particle, you need brackets around it, and there's a negative. Okay. Sorry, I can't add here, but that was supposed to be 14, and we did it. So that's good. All right, let's do next nitrogen dioxide. Let me grab my pen down here. So nitrogen dioxide, same basic idea. These are starting to get a little easier, but we have nitrogen with 5 plus 6. Of course, there's multiply that by 2, and we are going to be left with 17, which is no bueno, because that's an odd number. So what we got going on here, if we have nitrogen in the middle, we do 2, 4, 6, 8, 10, 12, 14, 16. We're already not cutting it here in several different ways. We're not making it. So what we could do then instead is take this and put that right there. So that would at least give us some sort of flexibility here. So let's try this here. So if we put 2, 4, a double bond, 6, 8, we got to take care of oxygen. We have 8 over here, 10, 12, 14, 16, and then that 1 right there, 17. If we look at this here, actually, we got oxygen happy, and because we have an odd number, this is actually the best we can do, because nitrogen has access to almost 8. 1, 2, 3, 4, 5, 6, 7. Now, if you look at nitrogen on the periodic table, because it's in the second period, excuse me, it can kind of be like boron. It can live in that sort of situation where it can go with less, just like the ones down below, like phosphorus, sulfur, selenium. the first example, they can live with more. Nitrogen can live with less, and that's what we have here. All right, let's look at another one. Oh, same one. The nice thing is this is a charged particle, nitrite particle. So if we take a look at this one, this makes it so much easier because 5 plus 6 times 2, and then we can add 1 to it, which gives us 18. And you're probably figuring out real quick what we can do then is just do a bond. I'll do it way over here just to kind of make it easier. There's 2, 4, 6, 8. There's that. Let's put a double bond, 10, 12, 14, 16, and then we can give that one 18. Now this is nice because everybody does have a full octet. Nitrogen can go with a full octet or cannot. And of course we would need our brackets around it and put that negative right here. Now you're probably saying, can that double bond move over here and form resonance? And the answer is yes, it can. You could draw a resonance to that. Of course, resonance is complicated because it kind of means multiple things. CNS is an easy one, so we have 4 plus 5, and that's plus 1. So this one's going to be a nice one here. We have 10. Let's just do this. Instead of doing, you notice we got 10 electrons. Then right away, it's going to be tough to expect 2, 4, 6, 8, 10. So right there, we're already at 8, and we need 10. So that's not good. If we did a double bond, that might work. 2, 4, 6, 8, 10. Or there's 8, excuse me. And then over here, that's not bad, but the best one to do, so that because nitrogen only has 6, if we can do it and we don't have an odd number like we did before, let's go ahead and do it this way. Let's say that triple bond 1, 2, 3, 1, 2, 3, N, and then we can just put a 2 over here and a 2 over here, and that's 2, 4, 6, 8, 10. And of course we'd have to bracket that up and put a negative